Good morning, everyone. My name is Jason Wesolowski. I'm the QA engineer here at TXRX. Today we're going to be going through an introduction to radio frequency basics. This presentation will take about half an hour, after which there'll be a 15-minute Q&A session. If you have any questions along the way, feel free to type them into the chat and we'll answer them as they come up. Actually, I should say we'll answer them at the end of the presentation.
So, yeah, and enter your questions in the question box. There's actually a question box for that. So this is Scott Galligan. I'm the inside sales manager. So Jason and I will answer the questions at the end. Go ahead, Jason. Sorry.
And we'll also be joined by one of our applications engineers, Mr. Jim Grotke. So without further ado, let's get into this. First, a little bit about TXRX. We're the industry leader in this area. We've been working with RF equipment since 1976, and we hold some of the original patents on combiners and TTAs. We have a dedicated applications engineering team. I mentioned Jim Grotke joining us. He's one of our engineers. This means that between the engineers and the proprietary design software that we've got, that we can mix and match all sorts of different filters to give the optimal performance for everything that you need for your sites. If you have any questions about if we can do something, we'll answer them for you. The third thing to know about us is that we've got a history of quality, reliability, and prompt delivery. We're ISO 9001:2015 certified. We have less than 0.1% warranty return. Typical lead time is about 4 to 5 weeks, 97% on-time shipment, and if we're late, we'll let you know. So enough about us. Let's start talking about some RF theory. In this presentation, we're going to go over some basic RF theory, RF wave theory, difference between dB and dBm, and some different modulation methods. We're also going to do an overview of the land mobile radio system with some diagrams, common terminology, and characteristic frequency bands. And finally, we'll end it with some typical test equipment and the applications for it. So, the first thing as far as wave theory is that all radio frequency energy travels as a wave. It's generated by electromagnetic fields. Anything within an electromagnetic field, such as a motor, power lines, generators, any of that can create RF energy. The RF signal can be absorbed or reflected by different materials. It can penetrate non-metallic materials, but it loses power. A good way to think of this is think about your cell phone when you're in a giant metal building. You got no signal in the middle of it. This is similar to how light works, just different frequencies, and of course different materials affect it differently. Since I mentioned frequencies, frequency is the number of waves passing a given point every second. And it's defined by a formula where the speed of light equals the frequency times the wavelength. So for 800 megahertz, which is a fairly common radio frequency, wavelength travels about 1.23 feet, or about 0.375 meters. In comparison, red light is about 700 nanometers, blue light's about 450 nanometers. They behave the same, but you can see there's a big difference in terms of the wavelength. Showing a diagram of this, think of it, you've got, in the first diagram, 2 waves over a 1 second period. In the second diagram, you have 4 waves over the same period. So the frequency of the first one is less than the frequency of the second one. So you'll hear a common term in radio work is dB and dBm. Let's talk about those for a minute. RF power is measured in watts. However, there's a big span in these power levels. You've got some transmitters that can be as low as a 1-watt transmitter, as high as 10,000 watts in some cases. So you've got a huge variation in the transmit power. The receive side of it is very weak generally because you're listening to someone that's miles and miles away. So the receive signal might be as low as 10 to the minus 15th. That's 15 zeros. Well, with so many zeros, it's hard to know whether or not you've got everything in the correct places, and you can easily make a math error. So instead of using watts, we use dBm. dBm is a logarithmic scale. There's no multiplication or division, only addition and subtraction in the dB domain. Instead of throwing in more zeros, we simply add 10 to the number every time we go up. Let's get a little more into this. dB is the equivalent of orders of magnitude, and it's a ratio. So in normal math, if A equals 10 times B, in dB math, A equals B plus 10 dB. At 100, A would equal B plus 20 dB. You'll notice that this is the number of zeros in the normal math method. So let's say A is 1,000,000 times B. Well, in dB math, A would equal B plus 60 dB. It should be remembered, though, that dB is a ratio, and it's not 0 dB is not 0. So if A equals B, then A equals B plus 0 dB. It means it's the same. Ratios are nice, but without a fixed point to know where to start, it's kind of meaningless, which is why we use dBm. dBm is how many dB greater than 1 milliwatt. So 10 dBm is 10 times 1 milliwatt, or 10 milliwatts. 30 dBm is 1,000 times 1 milliwatt, which gets you to 1 watt. 0 dBm, again, doesn't mean 0 power. It means you've got 1 milliwatt, because you're not greater than 1 milliwatt, you're at 1 milliwatt. This is all nice and good, but how do we get from watts to dBm and back? Well, it turns out there's a very nice formula to use with it. And if you want to get into the math, you can plug and play with these numbers. But as our two examples, if we have 10 watts, we plug through our formula and we get 40 dBm. Now remember what I said about 30 watts was 30, or sorry, 1 watt was 30 dBm. Now I've got 10 times the power, I'm at 40 dBm. Let's say I don't have 10 times the power. Let's say I only doubled the power. So I'm at 20 watts. Well, you go through the same formula and you get about 43 dBm. Turns out that if you're doubling the power, it's about 3 dB. If you're multiplying the power by 10, it's 10 dB. We can also convert back from dBm to watts using the reverse of this formula. So dBm is a measure of power. Its reference point is 1 milliwatt. You can kind of think of this kind of the same way as you've got temperature. 0 degrees C doesn't mean it's 0 heat. It means that's the reference point. So the same way, plus 50 dBm, you're at 100 watts. Minus 95 dBm, you're at a very small fraction of a watt. So how do we add power in this realm? Well, the first thing is we've got two signals coming together. We've got a plus 40 dBm signal on the left and a plus 40 dBm signal on the right. These are both about 10 watts of power. If we were to add this together as dBm, you would get 40 plus 40 is 80. And that would give you 100,000 watts. Clearly, that's not right. So what we do is we convert it back to watts. You have 10 watts plus 10 watts, it's 20 watts. If you remember, we did this math a few seconds ago, and that gets you 43 dBm. It is vitally important when you're adding power that you convert into watts and you don't try to do the math in dBm. So enough about dB and dBm. Let's talk about how we use RF waves. Well, we've got this thing called modulation. Modulation occurs when you've got three parameters of the signal that change. The first parameter is amplitude. Second parameter is frequency. The third parameter is phase. Now, you might remember some of these as AM and FM radio for amplitude and frequency. You don't usually see phase if you're a layman to this. There's also complex modulation, which is a combination of the amplitude, frequency, and phase modulations. Early example of this was actually Morse code. Morse code was an on-off signal, and it was 100% amplitude modulation. You were either transmitting or you weren't. But you could get a lot of information with just that little bit of variation on it. So amplitude modulation works by changing the amplitude or the power level of the signal. This is AM radio. If you've ever driven in your car with your AM stations on, though, you'll notice that anytime you go under any sort of power lines or near anything that might be generating, you get a lot of interference. Because of this, we tend not to use AM in land mobile radios, or at least not by itself. In this case, though, we've got a carrier signal, we've got a message signal. The combination of the carrier and the message creates this compound wave, and this is what signal is actually being transmitted by your equipment. The other one that everyone's familiar with is frequency modulation, or FM. This works by changing the frequency to carry the information. We ignore amplitude changes, and we have a better frequency range compared to AM. Now here, you can see that rather than changing the height of the peaks, we're changing the spacing of the peaks. Same idea, carrier signal, message signal, and the compound signal. The third modulation type is phase modulation, or angle modulation. And when the phase changes 180 degrees, you have two possible states. If you change the phase 90 degrees, you get four possible states. You can kind of keep shifting this phase to get more or fewer states available to you. We also mentioned complex modulation. This is a combination of AM and FM. Complex modulation is what really uses the backbone of telecommunications equipment. We've got coded signals. We've got more information because we're combining three different modulation types. A good example of this is the P25 phase 2 systems. You can see from our diagrams here, with the phase modulation going on, we've got 8 different states. That gives us 16 points. And we can do it either as frequency, amplitude, changing the phase, or any of the above. So how does this look when you've actually got your radio system? This is all nice theory. Let's actually put a radio together. But here's what your system looks like. Here's the hardware side of it. In this, we've got a receive antenna, which is sometimes hooked up to a tower top amplifier, not always. That pumps the signal down your tower to a receive multicoupler. The multicoupler spreads the signal out to your various radios or transceivers. Here you'll see we've got 5 different Motorola radios. Those radios will have their own signals going out. Those are pumped through a transmit combiner, and that combiner goes back up to your transmit antenna. And you'll notice that we've got subscribers over here to the right. The subscribers are the people that are receiving and sending those signals back and forth from the tower. They could be policemen, firemen, paramedics, some sort of security team that you might have in a warehouse. It could be military personnel. It could be people dealing with a sporting event. Either way, though, they're still using the same basic type of system. Getting a little further into this, we just showed you this portion here with the transmit and the receive sections, but this multi-coupler also has an internet connectivity. That lets you send emails to yourself, send cell phone messages, and it lets you do remote monitoring on your system. You can also rig various sensors to it, so that way the multi-coupler can send you any messages and you can feel the health of your system as it's working. So what else do we need to know? We mentioned there's some common terminology. First one is uplink versus downlink. In uplink, the subscriber is talking to the base radio. In downlink, the base radio is talking to the subscriber. And you can think of this as, are you going up to or down from the tower? Subscriber is on the ground, he's uplinking, he's talking up to the tower. The tower is talking down back to him. We also have conventional versus trunking. In a conventional system, if you have dedicated channels and if a channel is occupied, you've got to wait. In a trunking system, you have randomly assigned channels where the user is assigned the first available channel. Trunking systems, you can have more users talking at any given time, but the channels are not dedicated. There's advantages and disadvantages to both, which I'm sure somebody will ask a question on. Please do. The third thing is intermodulation. Intermodulation is what happens when you mix signals. Every time you get two or more signals that are colliding together, you create a new frequency that results from them. This is a big part of the land mobile radio system, and it's very important to reduce or minimize intermodulation as much as possible. And the reason is that if you've got two strong transmit signals that happen to combine and lay on top of one of those weak receive signals, you can easily swamp out the message that you're trying to listen for, and that's bad. So in land mobile radio, we've got 5 general radio bands that we're working with. The lowest one is VHF, which is between 150 and 174 megahertz. It's ultra or very high frequency. Then we move up to UHF, or ultra high frequency, which is 380 to 512 megahertz. Above that, we have a 700 megahertz band, an 800 megahertz band, and a 900 megahertz band. Now you'll notice that these 3 bands are not quite exactly 700, 800, and 900. There's a little bit of tail to each one of them into the next range band. So in the VHF spectrum, we have a terrible amount of disorganization. TX and RX are on separate frequencies generally, which is good. That's a duplex system, but sometimes you can't, so you have to put them on the same frequency. That's called a simplex system. Simplex only happens in VHF. Every other frequency band uses duplex for operation. I mentioned how disorganized this was, and this was because this was the early days of radio. It was kind of the Wild West. Everyone was grabbing whatever frequencies they could. No one really cared about what frequencies they had or didn't have. Because of this, it's a very congested radio environment. It's difficult to have a clean frequency plan for a system. You've got a lot of potential interference, and you can be very expensive to get enough filters or equipment to isolate your specific frequencies. Because of this, we've got complicated frequencies, we've got longer wavelengths, which means larger components in order to filter everything out. And of course, with size, you might have a physical space limitation. You also have a cost limitation to it. Moving up the scale to UHF. Now we start to see a little bit of organization that happens here. We've got downlink frequencies and uplink frequencies that are being separated. The good thing is that you can use off-the-shelf products for this. You have a better chance of a clean frequency plan, but we're still susceptible to some interference because we still have these frequencies interwoven with each other. We have a good example of the spectrum right here. You can see alternating downlink and uplink frequencies, and you might have some downlinks that are in one of these bands and some downlinks that are in a separate band over here. You might also have uplinks anywhere in the middle, or maybe you even have an uplink that's way out here on the other side. Moving into the 700 megahertz, now we're really getting organized. We have dedicated downlink and uplink frequencies. We have narrowband and broadband applications, and we're usually using some standard off-the-shelf systems, which means that your costs are going to be better. We have efficient filtering. We've got shorter wavelengths. Because of that, we also have easing the limitations on antenna placement. But we also have some wrinkles going on here. In particular, it's these new LTE FirstNet and Band 14 broadband applications. These are relatively new, but because they are broadband, you have to have a guard band in between them and some of the standard narrowband frequencies. Let's move up the chain though. Now we're in the 800 megahertz spectrum. And you'll notice, again, we've got a dedicated receive set and a dedicated transmit set. These are well organized, low interference. You can see that these frequencies are separated quite well from each other. Again, we're using standard off-the-shelf systems. We've got good filtering. So here's an example. You can see the spectrum starting all the way down at 746. This is the 700 band. And here at 806 is where we start this 800 band. And above 824, then we get into the cellular mobile bands. And we kind of drop back again. 851, we've got our transmit, to 869 is what our ending of the transmit bands are. And within that, we have different public safety, we've got expansions, we've got guard bands. Everything is nice and neatly organized within this range. But we went even higher, didn't we? We went all the way up to a 900 megahertz band. In the 900 megahertz band, again, we have some very strong organization. We've got dedicated receive and transmit frequencies. But we had a little bit of a alternation between narrowband and broadband that happened at 900 megahertz. So we have a little bit of a different treatment when it comes to that. The FCC has realized this, though, and they're trying to organize this 900 megahertz band into a whole series of narrowband and a whole series of broadband. Now, we've thrown those terms around, narrowband and broadband. Let's talk a little bit about them. Traditional narrowband applications are alive and well. Narrowband is used everywhere. Broadband is starting to come into play. Why do you want broadband? Well, you carry more data. Narrowband is still just fine for a lot of land mobile radio stuff. We mentioned that we've got new broadband applications. LTE was one of them that I mentioned first. We've got the 700 megahertz band and the 900 megahertz band, which both use heavy broadband applications. And this means that we've got some potential challenges, because when broadband is right next to narrowband, you can swamp out the narrowband if you're not careful. We need guards, we need to control our power levels, we need to control our intermodulation. This is all done by way of filtering, some active controlling as well. Make sure that nothing really steps on anything. And this is where our applications engineers can help you, by making sure that none of your frequencies step on any of the other frequencies in the area. We also have some remote monitoring and controlling capability. I mentioned this earlier, that you can have sensors hooked up to your multi-coupler. This gives you some digital features. We can put digital with analog. That's some really good stuff for the future. It gives you the ability to expand. We also have embedded sensors, so you can see just how well your system is working, and you can tell what's going on from the comforts of your own living room if you want. These are hooked up with Ethernet or SNMP. They can deliver you remote messages, emails, text messages, however you want to receive them. So you're out in the field and you don't necessarily have a healthy system. Let's say that your system is actually rather unhealthy. Let's talk about how you're going to diagnose it. You've got some common test equipment to see what's going on. First, you've got a spectrum analyzer, which measures and displays your power versus frequency. You've got a network analyzer, which is a bit more advanced. In this case, you're doing some responses of an RF device, such as losses and isolation. It might tell you if you've got a part of your system that's got excessive loss in it and it's causing you to have an issue. But for all this, sometimes you need a known good signal. So you also have a signal generator. It creates a perfect RF signal for the purposes of testing. You know what's going out, so you should know what's coming back. You can have a power meter for measuring incoming signal powers. You have different types. You can have a peak power versus an average power, and you can have power meters that read different modulations of the signals. Lastly, you have a site analyzer, which can inject a signal, measure the reflection, detect faults in your cable or in any of your amplifiers. In general, gives you a good feeling of the health of your system. So we know what's going on here. How are we going to get some key factors? Key factors. First thing, know your system's frequencies. Know how your system's frequencies interact. If they interact in different ways, then you have to account for and filter them through your intermodulation. Know your RF environment. And what do we mean by that? Well, you're not the only person transmitting and receiving a given tower. Most towers are fairly crowded. That means that you could have a lot of interference from anybody under the sun. So we offer two services that will help with this. We offer spectrum analysis, and we offer noise analysis. In this case, what we'll do is we'll come out with a trailer, we'll set up at your site, and we'll listen for 24 hours. And we'll figure out what else is in the area and who else is transmitting and receiving. The great thing is that this provides excellent data as far as what filtering you might need. It gives you minimum risk, so you don't have to worry about stepping on somebody else's frequency or them stepping on yours. Of course, if you work with us, we'll define what you need for a given system. We're always going to be trying to balance your system specs, your size, and your cost. It's commonly thought of you can't have everything you want, but we'll get you pretty darn close. Something to help with this, though, is that we have a questionnaire that will help you get what you need for that. And I'm going to hop over to it for a second. Here. On this questionnaire, you'll notice some basic information: company name, point of contact, name of the project. Are you expanding an existing system? It's a good question to ask. You might have a radio already in operation. Just go down a little further, though, and this is the meat and potatoes of what we need to know: what your frequencies are. Along with that, we've got some antenna information. We've got rack information, what type of power supply your system has, and any sort of thing going on in your environment. So let's get back to the presentation now. If you don't have all that wonderful technical info, what can you do? Well, you can make what's called a caveated design. which is that we will use our best practices, but we're going to have some assumptions in there. Once you get this design from us, you would need to validate it on site. You might even need to get it requoted. We just don't know enough. Of course, if you could give us this information up front, maybe with the help of one of the analysis services that we mentioned earlier, it gets us a more better feel for what you've got. And with that, we've reached the end of our presentation. We'd like to thank you for your attendance. If you have any questions, we will open up the floor and see what we can do to answer them.
And then there was one other question about low band. We do still, have some applications in the low band, 30 megahertz, to 80 megahertz roughly. We do have some products in those ranges. We don't have combining equipment, but we have duplexers and such in those ranges. So there are still some people that use those utilities and such that have some equipment down there. Are there any other questions that anyone has? I'd like to thank everybody for attending, and we will be having another webinar in another 6 weeks, so we'll send out information for that as well. Thank you very much for everyone, and have a great weekend.
Find out more at Vicom's website.